In this lecture, we are going to derive the Einstein relation, which is used quite commonly in solving numerical problems. We will take a semiconductor crystal which is kept in equilibrium. Since the semiconductor is in equilibrium, there will be no net current, meaning that current density due to electrons will be zero. Similarly, current density due to holes is also zero. We also know that current density due to electrons is equal to drift current density due to electrons plus diffusion current density of electrons. By writing the values of drift and diffusion current density, we will get here in this equation, n is the concentration of free electrons, q is the magnitude of charge on an electron, mu n is the mobility of electron, E is the electric field, and dn is the diffusion constant. And in the last lecture only, we found the value of electric field in terms of intrinsic Fermi energy level to be equal to 1 upon q into differential of intrinsic Fermi energy level with respect to x. We also know that the value of free electron concentration is equal to intrinsic carrier concentration multiplied by exponential of Fermi energy level minus intrinsic Fermi energy level divided by kT. Now, if we differentiate the free electron concentration with respect to distance x, then we will get intrinsic carrier concentration multiplied by differential of EF minus EI divided by kT with respect to distance x multiplied by exponential of EF minus EI divided by kT. It will give the differentiation of free electron concentration with respect to distance x to be equal to Now, in the last lecture, we discussed a very important point that for a semiconductor in equilibrium, the Fermi energy level EF is a straight line, meaning that differential of Fermi energy level with respect to x will be equal to 0. However, the same cannot be said true for intrinsic Fermi energy level. We will get the differential of free electron concentration with respect to x to be equal to minus free electron concentration differential of intrinsic Fermi energy level with respect to x divided by kT. Now, after putting the value of electric field and differential of free electron concentration with respect to x in the equation for net current density due to electrons, we will get free electron concentration and magnitude of charge will cancel out. The final result will be for final result of the equation to be equal to 0, one of the two factors in this equation must be 0. But since it is not necessary that the differential of intrinsic Fermi energy level with respect to x is equal to 0, therefore we will have mobility divided by q equal to diffusion constant divided by kT. And by rearranging the equation, we will get kT divided by q equal to diffusion constant of free electron divided by mobility of free electron. And you also know that kT divided by q is nothing but the thermal voltage. We had derived the expression for free electron concentration. However, similar expression can also be derived for hole concentration, which will give us thermal voltage to be equal to diffusion constant of holes divided by mobility of holes. And this particular relation is referred to as Einstein relation. One thing you should keep in mind that even though we have derived this relation for equilibrium cases, but experimentally it was found that this relation is also valid for non-equilibrium conditions. However, Einstein relation is not valid for degenerate semiconductors. This relation is valid only for non-degenerate semiconductors.